So chalo, we'll start the discussion. Last class we were talking about the performance of SJF. We have seen exponential averaging technique for predicting the next CPU burst time or next CPU burst. So essentially the advantage of shortage of first is it is optimal algorithm, it is the ideal algorithm but practically non-implementable. However, you can implement it with predicted burst times. And secondly, it is used as a benchmark to measure the performance of other algorithms to find out which algorithm practically implementable is closer in performance to shortage of first. I would like to discuss one PYQ, right? It's an interesting question. You can see it and then we go on to HRRN. I would be happy if you try to work out this gate question, previous gate question. FCFS is also non-preemptive. FCFS is also non-preemptive. Here they have written, they want minimum average waiting time, minimum average waiting time. This is the hint. The answer lies here. It is not that it is non-preemptive, you have to apply SJF. FCFS is also non-preemptive, am I right? FCFS is also non-preemptive. SJF, because SJF has the characteristic that it will give you minimum average waiting time. SJF will give you minimum average waiting time. Among all the scheduling techniques, the technique that gives you minimum average waiting time is SJF. It is optimal algorithm. So that's why we have to apply SJF. And SJF is non-preemptive. So because SJF can be preemptive and non-preemptive both, is it not? SJF can be non-preemptive or preemptive. So we have to apply non-preemptive because it is given in the question. So let's start. Let's start playing with SJF. Very simple chart. Time 0. The burst times are 16, 20 and 10. So naturally I am supposed to run P3 10 units. Then P1 16 units 26. Then P2 20 units 46. That's it. Average waiting time they ask. P1 has waited 10 units. So average waiting time. P1 has waited 10 units. P2 has waited 26 units. P3 has waited 0 units. Divided by 3. 36 divided by 3. 12. That's all. This is the concept. Got it? So as I mentioned, now I'm going to begin my discussion with the, we have seen 3, 4, 5, 5th scheduling technique now. And this is called highest response ratio next. Written in short as HRRN. Selection criteria is a parameter called response ratio. We will define this. Response ratio is defined as W plus S by S. Response ratio is defined as W plus S by S, where W is waiting time of process so far, waiting time of process so far, and S is the service time. If nothing is mentioned, you can take service time as burst time. Otherwise, service time generally, service time may also include IO burst, right? So this is W plus S by S. The mode of operation is non-preemptive because we are comparing with SJF, so non-preemptive. And the basic idea is, the basic idea of this, we'll write like this, favors not only shorter processes, but also limit the waiting time of longer process. Look at that. The basic ideology of HRRN is that it favors not only shorter process but also bound the waiting time of longer process. Because shortest job first inherently will have starvation to longer jobs. So I don't want longer jobs to wait quite long time. So favor shorter process, because favoring shorter process has an advantage. It will give you optimal schedule. Optimal means not only you can maximize the throughput, but also limit the waiting times and turnaround times. So favor shorter process, but at the same time, try to limit the waiting time of longer process. So how is it going to be done? That we have to see. So for that, I will take a data set and then I will show you first SJF, be on board. Let's take this data set, process number, arrival time, first time, 1, 2, 3, let's say 5 processes. Let's say their arrival times are 0, 2, 4, 6, 8, something like this. 3, 6, 4, 5, 2, something like this. Because we are comparing this algorithm with SJF, so essentially I will first prepare the Gantt chart using SJF. Then I will show you where exactly starvation is happening and then how that starvation to a certain extent is arrested by using HRRN. So let's prepare the Gantt chart. So first I will do for SJF, see on board. CPU. So this is the Gantt chart for SJF. The Gantt chart for SJF. Start at 0. Using SJF, which process do we start? So naturally we start with P1. Require 3 units, non-preemptive, complete at time 3. Now by time 3, only P2 has come, nobody else has come. So P2 runs for 6 units, non-preemptively, 9 it completes. Then by time 9, we have got P3, P4, P5, all of them are present. So among them, 4, 5, 2, which is shortest? P5. P5. 11. 9 plus 2. And then after that, P3 will run. P3 take 4 units, 15. And then lastly, P4 will run, 20. So boys and girls, here I would like to show you. Starvation. How starvation is going to happen here? Kindly observe. At time 9, P3 actually was available by time 4. When my time was 4, P3 was there. Just at 9, just before 9, at time 8, P5 came. P5 came just at time 8, just before 9, and got immediately favored. P3 came at time 4 but was not favored. P3 came at time 4 but not favored. It has waited long time. From 4 it waited up to 11. So I don't want this immediate favorism. This fellow came just now and got scheduled. So that is what I will write here. So this is favoring shorter process. Favor shorter process. And that is causing starvation to longer process P3. I don't want this behavior. So how HRRN is going to overcome this problem? I hope you are able to understand this point which I told just now. How shortage of first is favoring shorter process which has arrived just now, causing a long wait to the longer process. So I don't want that. So how HRRN is going to do that? So kindly see. I'll slightly squeeze this so that I can prepare the chart for HRRN. Be on board. So let's prepare the Gantt chart here. Let's prepare the Gantt chart now for HRRN. Be on board. I'll prepare the Gantt chart. This CPU. Time starts at 0. Please observe, at time 0, I have only one process. At time 0, I have only one process. So it does not matter whether you compute response ratio or not, because the paradigm of selection is response ratio. The paradigm of selection is response ratio. So I don't bother whether response ratio is computed or not, because there is only one process. There is only one process. So at time 0, we have P1, so we start with P1. No matter response ratio is computed or not, only one process. So what I am invariably trying to say that if there is only one process present in the system, scheduling does not matter. Scheduling criteria does not matter. Scheduling algorithm does not matter when there is only one process. So therefore, I start with P1 and complete at time 3. Again, at time 3 or by time 3, there is only one process P2. Only one process P2. So again, it does not matter whether you compute response ratio or not, because there is only one process. So therefore, like SJF, we schedule P2 completing at time 9. Now comes the difference. At time 9, we have got 3 processes, P3, P4, P5. So who should run? To decide that, I have to compute response ratio. To compute that, I have to basically compute response ratio. So here I will compute the response ratios. Please observe. So at time 9, what is response ratio RR of process 3? First I will compute for process 3. Formula is W plus S by S. What is W? Waiting time of process so far. Okay? P3 came, and listen boys and girls, P3 came at time 4. P3 came at time 4, and right now time is 9. So from 4 to 9, it has waited 5 units. Its burst time is 4, so plus 4 divided by 4, 9 by 4. Similarly, what is the response ratio of process 4? Process 4 came at time 6. Current time 9. 6 to 9, how much it has waited? 3 units. What is the burst time? 5 divided by 5, 8 by 5. What is the response ratio of process 5? Same way. 8 to 9 weighted 1 unit, plus 2 by 2, 3 by 2. So among these values, we can say this is nothing but 2 point something x. This is 1.5 on the 5 is 8, 3 means 5, 6 are 30, 1.6. This is 1.5. So response ratio of process 3 is higher, 2.25. Response ratio of process 3 is higher, not 4 and 5. So therefore, who will run? Process P3 will run. P3. Non-preemptive. Burst time is 4. So it is going to finish at time 13. 9 plus 4. At 13, can I make a decision immediately? No. Because waiting times may change. So we have to compute response ratio again. We have to compute response ratio again. So therefore I say like this. At time 13, I will recompute the response ratio of the processes pending. Who are pending? P4 and P5. So compute the response ratio of process P4. So I will write here response ratio of process 4. Process 4 came at time 6, current time 13, waited 7 units. 7 plus the burst time of P4, 5 by 5. 12 by 5. Likewise, response ratio of process 5. 8 to 13, waited 5 units. 5 plus 2 by 2. 7 by 2. This 12 by 5, 7 by 2. 12 by 5 means 5 2s are 10, 2.4, 3.5. So response ratio of process 5 is higher. So now process 5 is going to run, because shorter process, waited long time, 15. And lastly, P4 is the only pending process completing at time 20. I would like to draw your attention towards the fact that difference is here in comparison to this. Favored shorter process always. Here I will write like it has favored longer process. And then shorter process, then shorter. So it is going to maintain a balance like HRRN has maintained a balance somewhat in comparison to pure SJF. SJF always favor shorter process, favor longer and then shorter, because longer has waited quite good time, so favor it. Then later, shorter process also have waited quite a long time, so therefore we have favored shorter process P5. This is HRRN. Am I clear? Is this clear, boys and girls? How HRRN is going to balance the system by way of favoring shorter process and also limiting the waiting time of longer process. Very good. Very simple algorithm. No rocket science, nothing dive deep concepts. Very, very simple. Again, we'll proceed further and then we will go ahead with the next technique, which is again an important one. Somewhat similar to the ones that we discussed, and some questions were asked in earlier papers. So we will talk about it. Sixth in sequence. Priority based scheduling. Again, a scheduling technique which is practically implementable. Scheduling technique which is practically implementable and also used in many of the systems. What is the mode of operation here? Selection criteria. Selection criteria is nothing but the priority of the process. Priority is a value that indicates the level of importance of the process. Priority indicates the level of importance, how important the process is, priority. And mode of operation can be both. Mode of operation can be both non-preemptive as well as preemptive. And the tie-breaking rule we will follow tie-breaking rule we will follow as lower process ID. Right? We will follow like this. Let me tell you that, boys and girls, let me tell you that the principle of working of priority based scheduling is exactly similar to shortest job first. Boys and girls, 100% similar to SJF. Absolutely. So if you follow SJF, preemptive, non-preemptive, both, priority is almost done. 100% similar I am saying, except that in SJF we look at burst time. Instead of looking at burst time, I have to look at priority, that's it. That's the only difference, otherwise it is same. And in fact, I may not be wrong if I say shortest job first is also priority based. We are prioritizing the process having lower burst time. Is it not? So that is the point. So let me tell you something about the priority of the process. Let me tell you about priority. Generally, priority is assigned as some integer value. Priority is assigned as an integer value, and this value essentially is computed by applying some function. Actual implementation I am talking about. The operating system scheduler will use some function. The parameters of the function is like type of process, or maybe number of resources that the process is using, and size of process, etc. So many other parameters. So by taking different parameters, the operating system scheduler would compute the priority by giving weightages to these parameters. Meaning, type of process I said, like OS process will have high priority, user process will have low priority, interactive process high priority, background backup process low priority, faculty process high priority, student process low priority, like that. Then size of process. If the process size is large, long process, low priority, short process, high priority. Why? Because it will run for some small amount of time on CPU, short process. Process need more resources, low priority. Process need less resources, high priority. So like that, we use some parameters and have some formula and compute the priority. In general, I told the principles. When do we have high priority, when do we have low priority, like that. So priority is generally taken as an integer value. And let me also tell you that the priority which we assign can be of two types, static or dynamic. static or dynamic. Static priority means once we assign the priority, the process priority is not going to change. It will remain static. We cannot change the priority. Priority which is assigned at the time of creating the process, it will remain the same throughout its completion. It cannot change. So inherently, what is a drawback that are we going to get with static priority? What is a drawback? The drawback with static priority naturally will be starvation. Starvation to whom? Those processes which have low priority. Low priority processes would be definitely suffering from the problem of starvation when I go for a static priority. Okay? To overcome the problem of starvation, we go for dynamic priority. So what is going to happen in dynamic priority? Priority changes. Changes generally increases at regular intervals. Changes at regular intervals. At regular interval of time, the priority of the process increases, changes, so that eventually a low priority process would become high priority process after good amount of time. Low priority process would become high priority process after good amount of time. That is dynamic priority. Because we are changing the priority, we are increasing the priority of the process. That is why this dynamic priority, where we are increasing the priority, is also sometimes called as aging algorithm. Aging algorithm. I'll work out the questions for both static and dynamic so that you can have some clarity of understanding. So, but re-emphasize here that priority algorithm is 100% similar to SJF working, shortage job first, and SRTF, non-preemptive and preemptive. Except that in SJF we look at burst time, here we have to look at priority. That is the only difference between both. Come on. So what I will do, another important point I have to tell you, thereafter I will take a data set and first you are going to work out, then you can compare with my answers. See, boys and girls, one important aspect. When I say priority is assigned as an integer value, so I can have two conventions. Higher number, higher priority, lower number, lower priority. This I call natural convention. Means if the number is high, that is high priority. If the number is small, low priority. But sometimes they follow reverse convention. They say that lower number, smaller number, high priority, and larger number, low priority. So convention can be anything, you don't have to get misled. Let me tell you that in the exam or in the question, they will clearly specify this also. What is a convention? Smaller number, higher priority or lower priority, they will tell you. I follow for my problems. For my problem which I am doing, I follow natural convention. Higher number, higher priority, lower number, lower priority. So what I will do, I will give a simple data set. First, you solve the problem. Make sure that you understood and then you can compare with my answer. Okay, so let me give you the data set. Let's say process number, arrival time, burst time, priority. 1, 2, 3, 4. I'll take only 4 processes. Arrival time 0, 2, 3, 5. Burst time, let us say 6 or say 4. Okay, and then 3. Then 2, then 5, 6, 8, 10, or I will reverse it. Come on. Higher number, higher priority, lower number, lower priority. With that convention, you prepare the Gantt chart for both. After drawing the Gantt chart, I want you to tell what is the average turnaround time and average waiting time? Average turnaround time and average waiting time. This you have to tell of both preemptive and non-preemptive scheduling. I am doing it here for non-preemptive first. Have a look, please. I am drawing the Gantt chart first for non-preemptive. Here I am drawing. So let's say non-preemptive priority, time 0. Only one process P1. Burst time 4 units, non-preemptive, completes at time 4. By time 4, if you observe, P2 and P3 have arrived. Only P2 and P3 have arrived. So therefore, among them higher priority is whom? P2. So we schedule P2. We schedule P2. Non-preemptive, completes at time 3 units, means 7. Now by time 7, everybody has come. So next we schedule P4, having burst time of 5 units, so 12. And then P3, having burst time of 2 units, so complete at time 14. This is non-preemptive priority based. The average turnaround time if you compute, P1 4 minus 0 4 plus P2 7 minus 2 5, P3 14 minus 3 11, P4 12 minus 5 7 divided by 4. This is 9 20 27, 27 by 4, 4 6 24, and then 24 means 3 7 5, 6.75. Average waiting time, right? P1 4 minus 4 0, 5 minus 3 2, P3 11 minus 2 9, P4 7 minus 5 2 by 4, 10 11 12 13, 13 by 4, 3.25. Average waiting time is 3.25. Yes. Now if you go for preemptive version, if you draw the Gantt chart for preemptive version, so what is going to happen? We'll draw the Gantt chart for preemptive priority. This CPU 0. We start with P1. P1 is going to run for 2 units. 2 units. Because at time 2, P2 come with priority 10. 10 is greater than 6. 10 is greater than 6. So preempt in favor of P2. P2 continues till 3. But low priority process come. Low priority process come. Is it not? 8. 8 is less than 10. No preemption. So P2 will continue. P2 will continue till, look at that, from 3 to 5. 5. 2 to 5 means it has run basically 3 units. It has run for 3 units. Is it not? Its burst time is over, right? 3 units is its burst time, and burst time is also over. Who? P2. So P2's burst time is over. Now what happens by time 5? By time 5, you can see P4 is there, P4 has come, and it is having the highest priority. So therefore P4 will take the charge. P4 will take the charge. P4 need 5 units, so directly it will run all 5 units, 10. Then after that, who will run? So balance process are P3 and P1. P3 and P1. P1 priority is 6, P3 priority is 8. So naturally P3 is higher, so P3 will run for its total 2 units, so 12. Now the balance of P1. P1 is the lowest priority. It has basically how many units left over? 0 to 2 earlier it has run, so another 2 units. So it completes at 14. It completes at 14. This is the chart. So now if you calculate average turnaround time, P1 completed at 14, P2 completed at 5, 5 minus 2, 3, P3 completed at 12, 12 minus 3, 9, P4 completed at 10, 10 minus 5, 5, divided by 4. So 14 plus 3, 17, 17 plus 5, 22, 31, 31 by 4, 29, 30, 31, 3, 7.75. So 6.75, 7.75, and like that you can calculate average waiting time, preemptive version, and see the comparison. So this is priority based scheduling. There was a direct question in one of the GATE paper based on priority based scheduling. I would give that question. You are again going to work out, but do it please. So let us take one example. Work out this problem, please. This is a previous gate question, numerical answer type question. I will prepare the Gantt chart here. CPU, time 0. 0, we start with P1. Next arrival time, look at that. Next arrival time is 2. Priority of P1 is 2. And then 0 to 2 it runs. 0 to 2 it runs. Where I receive P4 with priority 1. 1 is greater than 2. So preempt. Preempt P1. In favor of P4. In favor of P4. Now P4 continue to run till, see that, after 2 the next arrival time is 5. 5. So 2 to 5. 3 units. At that time, look at that, at time 5 I receive P2 with priority 0, that is highest, so preempt. So P2 take the charge. P2 being highest priority, it is not going to get preempted by anyone else, so it is going to run till completion, all 28 units, 28. So 5 plus 28, 33. 28 plus 5, 33 units. P2 completed, right? P2 completed. So now after 0, next highest priority is 1, so that is P4. P4 will take the charge because all other processes have arrived. P4 balance is how much? Earlier P4 ran for 3 units, 2 to 5, 3 units. Its balance is 7. So it is going to finish at 40, P4. So 0, 1 over. So this process is over, this process is over. Next highest priority 2, P1. So P1 will run. Earlier P1 ran for 2 units, balance is 9, 49. 49. So 2 is also over. Next highest priority 3, that is P3. P3 earlier has not run. P3 need 2 units, so complete at 51. 51. So P3 is also over. Then last process is P5. P5, lowest priority, P5. Its burst time is 16 units. 16 means 67. 16. Average waiting time. P1, see, P1 came at 0, 0 to 2, no waiting, but 2 to 40 it has waited here, 2 to 40. How long? 38 units. P1 has waited 38 units. Then P2. P2 came at time 5, got scheduled at 5, no waiting for P2. 0. P3. P3 came at time 12. It came at time 12. It got scheduled at time 49. It got scheduled at time 49. P3, look at that. P3 came at time 12, got scheduled at 49. So 49 to 12, right? 12 to 49. So 7, 37. 37. 37. Plus P3 over. Then P4. P4 came at time 2. So here there was no waiting for P4. Here there was no waiting. But here, so from 2, from 5, look at that. 2 to 5 it has run, no problem. But from 5, again it got scheduled here. Again it got scheduled here at 33, P4. So 33 to 5. 33 minus 5 is how much? 33 minus 5, this will go 8 and this 28. So this will be 28. 28. Plus. Last now P5. P5 came at time 9, look at that. P5 came at time 9 and from 9 it got scheduled at 51. So therefore 51 minus 9, right? 42. Correct? So waited 42 units. Divided by 5. So if you add up all, right? If you add up all and divide. So it's saying average waiting time of all the processes using priority based. It is not asking to round off, is it not? In milliseconds. So you are supposed to take as it is. So is it 144 or 148? 140. Why different people are telling different answers? Let me calculate the sum. Let me calculate the sum myself, because again for that also people are telling different answers. 38 plus 37 plus 28 plus 42. 145. This is 145 divided by 5. 29 is the answer. Exact 29. So I'll take the most important problem, the star problem of priority based scheduling, which I really like very much. So this is one of the star problem of previous PYQ, previous gate question. Let's try reading the question first. Consider a system with preemptive priority based scheduling with 3 processes P1, P2, P3 having, look at this, having infinite instances of them. What does this mean? That means I am having a continuous stream of P1, many instances of P1, 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 infinite. Okay, fine. The instances of these processes arrive at regular intervals of 3, 7 and 20. That means starting from the first arrival, first instance, at regular intervals of 3 units P1 comes. Imagine if P1 comes at 0. So next instance of P1 comes at 3, next at 6, 9, 12, 15, duration of 3 units. The period of arrival of next instance is 3 for P1, 7 for P2, 20 for P3. Got it? That's the meaning. The only, in this question, the only point that you have to understand is this. The priority of the process instances is the inverse of their period. The priority of P1 is 1 by 3, P2 is 1 by 7, P3 is 1 by 20. Okay? Each of the processes instance P1, P2, P3 consume 1 to 4 millisecond of CPU time. Burst time is 1, 2 and 4. The first instance, look at that. The first instance of each process is available at 1 millisecond. It is not 0, 1 millisecond. What is the completion time of the first instance of process P3? When does first instance of P3 complete? Very interesting question. One of the question which I like very much, right? Earlier occasion also I gave one problem in shortest remaining time first. That is an interesting one, and this is also first come first serve earlier, which we have solved using what I call using IO burst times. So after that question, this is also an interesting question, very interesting. So let's try to work out. Let's try to work out. I will organize the data set first, boys and girls. So here I will write process number, arrival time, burst time, right? And here I will say period of arrival, and here I will say instances, arrival of the instances. P1, P2, P3. First arrival of the instance is time 1. The burst times of each of them is 1 to 4. 1, 2, 4. Period of arrival 3, 7, 20. So based on period of arrival, we can calculate the priority. Priority is reverse of it. So here I will write priority. Priority of P1 is 1 by 3, 1 by 7, 1 by 20. So 1 by 3 is highest, this is lowest. 1 by 3 is a higher value, is it not? 1 by 20 is a lower value, so lower value, lower priority. Now instances if you mark, look at this. The first instance of all processes at 1, next instance of P1 will come at 1 plus 3, 4. Next will come at 7, next will come at 10, 13, 16 and so on, it goes. Duration of 3 units starting from 1. Starting from 1, duration of 3 units, like that. Starting from 1, duration of 7 units. So 1 plus 7, 8, 8 plus 7, 15, 22, 29 and go on. Third, first instance at 1, next 21, next 41, next 61 and so on. Have you got the data like this? Were you able to interpret the data in this fashion? Okay, very good. Now I told you now, I mean lower priority, lower value. That is the default convention. The arrival frequency you can consider. These are arriving at a very fast frequency. Period is 3, so that should be high priority. That is the logical implication. These are arriving at a very low rate. So lower rate means lower priority. That is the implication. Okay, chalo, we will draw the Gantt chart. We'll draw the Gantt chart. Please see on board CPU. Listen, 0 to 1 is idle, right? Let us say this is a ready queue. This is a ready queue. So 0 to 1 is idle. Now at time 1, I will mark like this: P1 first instance is available, P2 first instance is available, P3 first instance is available. Subscript indicate instance number P11, P21, P31 like this. So among them, the highest priority is P11, so therefore P11 is going to run for 1 unit and complete. That means at 2 it completes. Now who will run? P2 and P3, the highest priority is P2. So P2 is going to run, first instance. P2 need 2 units of time. Can it run for all the 2 units? Yes, it can run 2 to 4. P3 is lowest priority. Now at time 4, observe, P3 was about to take the charge, but suddenly at time 4, P1 comes. P1 second instance comes. And that is higher priority. So therefore it is going to take the charge. So it is going to take the charge. P1, 2. 5 units it completes. 5 units it completes. Now at this time, at time 5, we have got only P3, first instance. It actually needs 4 units, but can it run 4 units? No, it can run only for 2 units. Why? At time 7, P1 comes again, P1, third instance. And it is going to preempt P3. P3 goes back to the ready queue, giving the control to P1, third instance. Run for 1 unit, 8. Again at time 8, P3 was about to take the charge, but suddenly at time 8, P2 new instance comes, P2 second instance. And that is having higher priority than P3. So P2 second instance runs. How long? 2 units. 2 units at time 10. Suddenly at time 10, a new instance of P1 comes again. Check at time 10. P1, fourth instance comes. So that will take the charge, fourth instance. It need 1 unit, so 11. Now P1 is also over. Who is remaining? Only P3 is remaining. Next instance of P1 comes at 13. Next instance of P2 comes at time 15. Look at that, time 15. And therefore only P3 is available. So now P3 first instance balance is 2 units. So it could run 2 units successfully. It could run 2 units successfully. This is the chart. So first instance of P3 got completed. First instance of P3 got completed at time 13. So therefore the correct answer is 13. So the answer for this question is 13. Completion time of the first instance of process P3. So we'll see the other questions slightly after some time. There is one more question on priority, I suppose. Very important technique. One of the important technique among all the topics, round robin. Round robin. Basically used in multi-programmed MPR plus time sharing systems. System that share the time of CPU. Time sharing systems. Like Unix. The initial version of Unix, they used to use pure round robin. Selection criteria is arrival time plus time quantum. We write in short TQ. Some people say time quantum, some people say time slice. Both are same. Selection criteria. Mean the processes are maintained in the first in, first out order, right? Like FCFS. But unlike FCFS, this mode of operation is preemptive. Mode of operation is preemptive. Mode of operation is preemptive. Tie breaking rule, again you can say lower process ID. Lower process ID. And here I will tell you the working mechanics of it. Each schedule process is allotted a time quantum within time quantum. If the process completes or needs IO, then will leave CPU. Otherwise, it gets preempted. Otherwise, it gets preempted. This is the ideology. So what I do is, point number one, boys and girls, please follow me. Point number one, the processes are maintained in ready queue in FIFO order, first come first serve, like first come first serve algorithm, FIFO order. The ready queue follow FIFO discipline. All the processes are maintained in FIFO order. We start with the first process which is there at the front of the queue, but we are not going to run till completion like FCFS because this is preemptive. So every process scheduled on CPU is allotted a fixed time quantum or time slice. Within the timer, within the time slice, if the process complete or need for IO, it will leave the CPU. But if the process doesn't get completed or doesn't go for IO within the time slice, then after the time slice is over, the hardware timer interrupt comes. Hardware timer interrupt comes, causing the process to get preempted. Causing the process to get preempted. Why? We have given enough time to this fellow. We cannot hog on the CPU with this process. We want to improve interactiveness. We want to give the chance to other process. The basic objective of round robin is to improve interactiveness. Give the fair chance to other process. Every process should not be allowed to run for indeterminate time, fixed amount of time. So if time quantum expires, process get preempted. The preempted process will be added back to the queue at the end, because this is a FIFO queue. At the end, it will get added, and next process in line is taken up. And this way we continue in a round robin fashion until we complete all processes. This is the basic idea of round robin. So because it is working on arrival time, that is why some people even call round robin as preemptive FCFS. Because the processes are maintained in FIFO order. So that's why some people even call this as preemptive FCFS. Preemptive FCFS. So this is the notion, this is the idea of round robin. Right? So summarizingly, I tell, processes are maintained in FIFO order. Every scheduled process will get a fixed time quantum. Within the time quantum, if it completes, well and good. If it doesn't complete, time quantum expire, process get preempted, put back to the queue. Next process in line from the queue is taken and scheduled. And this way we continue until all processes finish their execution. This is the notion of round robin. So what I will do is, I will give a data set. You are going to work out first, and then you can compare with my answer. So I'll give you this data set for which you can work out, and then you can prepare, you can see the answer with my solution. Let's say the following: process number, arrival time, burst time. First I will take a normal data set. Then I will take a different arrival time, 0, 0, 0, 0, 5, 4, 2, 3. Time quantum is equal to 2 units. I want you to compute average turnaround time. I want you to compute average turnaround time, average waiting time, and average response time. Come on, do it please. So here I am showing ready queue. Ready queue is mandatory for this round robin. Other scheduling technique you can draw it without ready queue, but for round robin, ready queue is compulsory. At time 0, all processes are there in the ready queue in FIFO order. So P1, P2, P3, P4. So who will run start? P1 will start at 0. How long it runs? 2 units. Total requirement 5. It runs for 2 units. Preempt and put back to the queue. Look at that. I am putting it back P1 here. Then who will run? P2. P2 will run for 2 units. 4. 2 to 4. It get preempted. Add back to the queue because it has not completed. 4 units it need. P3. P3 need 2 units. Time quantum is also 2. So P3 completes at time 6. P3 is over. I don't need to add P3 back. Next P4 runs. P4 runs for 2 units. 6 plus 2, 8. It get preempted and back to the queue. It has not completed. So I add to the queue. Next P1 will take the charge. P1 will run for another 2 units, 10, 8 plus 2, get preempted because it need 5. So again add to the queue. Then P2 take the charge. P2 earlier ran for 2 units, another 2 units it runs and completes. P2 is over. Then P4. P4 earlier ran for 2 units, balance is 1, so it completes at time 13. And finally P1 need 1 unit, it completes at time 14. This is the chart. So you can calculate average turnaround time. So here I will calculate average turnaround time. P1 completed at time 14, so therefore 14. P2 completed at time 12, so 12. P3 at 6. P4 at 8, sorry 13. P4, that's it, divided by 4. So this is 26, 32, 35, 45. 45 divided by 4. 11.25 average turnaround time. Come on. P1. So 14 minus 5, 9. 14 minus 5, so 9. But turnaround time minus burst time. So 14 minus 5 if I take, so it become 9 plus 12 minus 4, 8 plus 6 minus 2, 4 plus 13 minus 3, 10 divided by 4. So 17, 27, 31, 31 by 4, 31 by 4. 7.75, 7.75. What is the response time, average response time? Let us calculate here. Let us calculate average response time here. Come on, what is it? P1 average response, P1 response time is 0, P2 is 2, P3 is 4, P4 is 6, divided by 4. So 6 plus 6, 12 by 4, 3. It is 3. What I want you to do is, please observe, what I want you to do is, repeat the problem for first come first serve. Because we are saying this preemptive FCFS, so non-preemptive FCFS. Repeat the problem for FCFS. Repeat the problem for FCFS and let me know average turnaround time, waiting time and response time. Particularly response time. What is the response time we would like to compute? If you repeat the problem with first come first serve, so let me write 5, 4, 2, 3. Five, 4, 2, 3. CPU. So I am doing this for first come first serve. So quickly I'll put the values. So you can compare the answers. 9.75, their average turnaround time 11.25. 6.25 waiting time 7.75. But response time 6.25, their response time is 3. Response time is better. Response time is better. But average turnaround time and waiting time in round robin is increasing. Waiting time is increasing. Turnaround time is increasing more. Why? Because I have more context switchings. Right? More context switches. So that's why it waits. The average waiting time of FCFS is better. Average waiting time of FCFS 6.25, response time 6.25. But the advantage of round robin, as you see here, is better responsiveness. Process number, arrival time, burst time 1, 2, 3, 4. Arrival times I will take differently. Take time quantum is equal to 2 units and repeat the problem, please. Compute average turnaround time and waiting time. Again, average turnaround time, average waiting time, average response time. So let's start. There is a slight thing I want your observation here. We start at time 0. In ready queue I have only one process P1. So we start with P1. Requirement is 7 units. Time quantum is 2. It is going to run till 2. Now exactly at time 2, please observe, exactly at time 2 P2 comes. And P1 should also be trying to go into ready queue. So P2 is trying to come into ready queue. P1 is also trying to come into ready queue. Here again we have a tie. We have a tie. So doubt arises, question arises, who should be added first? Are we going to add P1 or are we going to add P2? Again I repeat, at time 2 when preemption is happening, timer interrupt has come and preemption is happening, P1 is trying to go into ready queue and at the same time new process P2 is also trying to come to ready queue. So at time 2 there is a tie between P1 and P2. Both of them want to enter the ready queue at the same time. The question arises, who should be added first? The basic objective of round robin, please observe. The basic objective of round robin is to improve interactiveness. Or improve responsiveness. Is to improve interactiveness or responsiveness. That means the processes should be given fairer chance to run. So here an argument comes. P1 has already got a chance to run for 2 units, already got a chance. Now P2 has come. So new process, it has not got the chance. So if I give the chance again to P1 and then P2, P2 will not be interactive or will not become responsive. So with an intention of improving the interactiveness or responsiveness, I should give favor to new process, not the old process. Because old process P1 already got a chance to run on CPU for 2 units. So let new process be given the chance. Then only the system become interactive or responsive. So here, instead of lower process ID, with an intention to improve performance, let us say we give preference to new process. P2, then P1. To make the system more interactive or more responsive. That is the argument. But in the exam, again I am repeatedly telling, they will give you the tie-breaking rule, what should happen, right? So in that situation, if whatever they say, you follow it. Here I am following. In respect of interactiveness, I will give chance P2 P2. So P2 runs 2 units, 4. In between 2 and 4, P3 has already joined, so I add P3. Now for P3 there is no doubt, no problem. Because at time 3 it came. Now at time 4, P2 get preempted, add to the queue. Next, who will run? P1 will run. P1 will run for 6 units. 4 to 6 there is no new process. 4 to 6 there is no new process. P1 still has more burst time, so P1 gets preempted and add to the queue. Next, who will run? P3. P3 will run. P3 exactly need 2 units, so complete at time 8. Complete at time 8. No preemption, no adding. Next, P2 will take the charge. P2 earlier ran for 2 units, so another 2 units it will run, 10 it completes. But between 8 and 10, new process P4 has already joined the queue, so add. Then P1 will take the charge. P1 earlier ran for 4, so another 2 units it run, 12, and add to the queue, P1. Then finally P4 runs, 1 unit it needs, P4, so it completes at time 13, and then finally P1 needs 1 unit, completes at time 14. This is a Gantt chart, assuming the point which I told earlier. But I will show you the other chart also, lower process ID. With the concept of lower process ID, what is going to happen? We'll work out that also. Please see on board. I will work out with lower process ID also, see on board. So here I say second instance, I am working out with lower process ID. What is the difference? Okay, this is ready queue. This CPU, time 0. Let's start. So time 0 we have got P1 as usual. So P1 is going to run for 2 units. Lower time to conflict, so therefore again P1, then P2. So P1 is going to run 4, correct? And then between 2 and 4, P3 has joined the queue already at time 3, and then I preempt P1 and put it back to the queue. Correct? Then P2 take the charge. P2, 6. Between 4 and 6, nobody has gone, so P2 get added. Then P3. P3 need just 2 units, 8 it completes. Then P1, so therefore it runs till 10. In between 8 and 10, you can see P4 has joined already, and now P1. Then P2 runs. P2 need only for another 2 units complete. Then P4 runs, 1 unit it completes. Then P1 run, 1 unit it completes. This is the chart. This ordering is very important. If you don't maintain this order, you will go wrong. This ordering is very, very important, boys and girls. Based on this order I have scheduled. See here, 0, 2, at time 2 P2 came, so therefore P2 got added, then P1 got added. Then after P2, P1 run, right? Then after, in between 4 and 6, P3 has come already. Right, in between 2 and 4 already, when P2 got preempted, P3 has already come, so I added P3, and then P2 got inserted here. So after that P1 runs 4 to 6, no new process, so therefore P1 get preempted, add to the queue. That's why P4 got scheduled after P1. That is the reason. Prepare the chart. I will draw the Gantt chart again to clear your doubt, because you are not following my point. Please follow this. This is very important. Boys and girls, please have a look. Again I am doing CPU, ready queue. First approach I am doing again. Where this paradigm. Time 0, we have got P1 alone. I start with P1, 2. Correct? So at time 2, what did we said? P2 came, P1 getting preempted. So I am adding P2 first, I said. And P1 should get preempted, added back to the queue. P1 get added. Is this clear? Okay. Now what happens? Continue. So who will run? P2 will run. P2 need 4 units, time quantum 2 units, so it is going to run till 4. But in between, listen, in between 2 and 4, P3 has come. P3 has come. So therefore, P3 will get PT. It is a FIFO queue. New process will get added at the queue. P1 was already there. Now P3 gets added after P1. Added after P1. Right? And at time 4, P2 get preempted. So P2 gets added here. Is this clear? So what I want you to do is, with both the approaches here, with these both approaches, I want you to tell me just average response time. What is average response time here? What is average response time here? Please tell me. Just calculate average response time of both the Gantt charts, both the approaches, and tell me which is better. Are both same or different? We will see. Are both same or different? We will see. Come on, boys and girls. So I will compute the average response time for the first case here, average response time. And here we will compute average response time. P1 is 0. P2 is 0. P3, 3 to 6, 3. P4, 9 to 12, 3. Divided by 4, 6 by 4, 1.5. Am I right? Average response time of the first case. Second case, P1 0, P2 came at time 2, got scheduled at 4, so 2 units. P3, 3 to 6, so 3 units. P4, 9 to 12, again 3 units. By 4, 8 by 4, 2 units. So that is what I said. What did I say? I said the same thing. Remember, this is much better responsive. This is much better responsive. 1.5 is better responsive. Response time is less because we have given the chance to P2 first, not P1. Therefore, the first system is more interactive, and the basic objective of round robin, I said, is to improve the interactiveness of the system. That is the reason I said favor the process, not lower process ID, but the one who has come first with an intention to improve the responsiveness. I hope you are able to understand my point, why I have done this way, not this way. You understood the mechanism? Now before we close, I will give one more data set, simple data set, you try it. Or maybe I will give a direct PYQ, then you can try. Simple gate question, PYQ, simple gate question, 1 mark. Ready queue. We have processes A, B, C, D in the order. Time quantum is equal to 1 unit. 0 plus, some people get confused here. Sir, what is the meaning of 0 plus? We write 0 plus. 0 plus means nothing but, this is actually the timer. This is actually the timer. This is actually the timer. 0 it actually starts. 0 plus means the moment when it starts clicking, when it starts working, 0 plus. That is the meaning. When it starts, so the 0 plus is definitely nothing but 0 only. 0 only. So this CPU, time 0, we have order A, B, C, D. Each process take 1 unit of time. 4181. So therefore, when I have scheduled all the 3 processes, B and D get completed. B and D get completed. So we will have only A and C, right? So A, C, again C. A need 4 units. 1, 2, 3, another one. A completes here. So 5, 6, 7, 8, 9. That's it. This is the completion time of process A. They ask this. Then in the next class agenda, I will tell you, I am going to work out few more problems on round robin and also other scheduling techniques, PYQs. Okay. So please work out all the questions left over in the handout as practice, as homework. We'll discuss them in the next session. Take care. Good night. Thank you very much.